Okay, so as I usually do, we're just going to briefly review to help you guys understand what's going on in the class. I know we've had a long break, so welcome back, everybody. So we've been talking about Chapter 8, which is internal flow. So flow through a pipe or through a channel. There's some pretty interesting stuff and actually some pretty important concepts that are contained in this chapter that are probably things you'll need to remember your whole career, especially if you get into process engineering, especially this concept of the log mean temperature difference, which we'll go through and derive today. So internal flow is flow through a pipe. If you remember, we still have boundary layers that form as the fluid enters the pipe, but eventually those boundary layers will converge into each other and you'll get what's called fully developed flow. So once you get fully developed flow, basically your heat transfer coefficients will level off and they'll just be constant from the point of starting with the fully developed region all the way to the end of your channel. So we might have to deal with things like local heat transfer coefficients at the beginning of the pipe, or if the pipe is quite long, then we can neglect what's happening at the entry region and just treat our heat transfer coefficient as being constant throughout the length of the pipe. So we'd basically be neglecting that entry region. Okay, so we talked about something called the mean velocity, and we also talked about a mean temperature. So while, even after the flow becomes fully developed, there is still a velocity profile where the velocity changes as a function of radius if it's a circular pipe, and there would also be a temperature profile. However, we sort of neglect those by just treating them as the mean velocity or the mean temperature. So basically, when we talk about the mean velocity or the mean temperature, we're just assuming that all of our analysis can be done by just taking the average fluid velocity or fluid temperature at a particular distance down the length of the pipe. So we're neglecting these radial variations. So a lot of if it's a pipe that is not circular, we'll use something called the hydraulic diameter of the pipe, which we would use to calculate things like Reynolds number, which is going to be critical for the correlations that we'll use. So the hydraulic diameter is defined as 4 times the cross-sectional area divided by the wetted perimeter, anything that's touching the fluid. Okay. So one of the important things that we got to was this idea of figuring out what the mean temperature is. When we introduced convection and when we talked about convection in the context of conduction problems, we treated convection very simply. It was just Newton's law of cooling, that Q is equal to H times A times delta T. That gets complicated now when you have flow going through some kind of a channel because the fluid itself changes and it might heat up or cool down as it goes down the length of the channel. So that means we have to come up with other ways. That simple version of Newton's law of cooling doesn't quite apply, and that's because your delta T isn't constant as a function of distance down your pipe or your channel. So we looked at how do we figure out the mean temperature when you have constant flux in your pipe. So we did this with a differential energy balance. If you had a fluid coming in at some inlet temperature, so you have this T, M, I, so that's the mean temperature at the inlet. It's going to come in at that inlet temperature and it's going to be heated continuously as it goes down the length of the pipe. And if we're applying a constant flux, that means our temperature is just going to increase linearly as it goes down the pipe. And we were able to actually solve that by doing a differential energy balance. And by solving that differential energy balance, separating and integrating, we were able to get our temperature profile, which is this sloppy looking equation here at the end. But really, it would look like this. So that's just the equation of a straight line. So we'd basically see our mean temperature rise linearly because we're applying this constant amount of heat flux to it. Any questions so far? I know this is review, but I'm trying to help us all get back in gear after the fall break. Okay, so there is another condition. Rather than applying constant heat flux over the length of the pipe, what if we just maintain that pipe at a constant surface temperature? So now we have to deal with actually Newton's law of cooling directly. So remember that delta T is our driving force for heat transfer. So we did this differential energy balance, only instead of having a constant Q, we actually had Newton's law of cooling show up in our equations. So what we found was that at the beginning of the pipe, there's the biggest delta T. So delta T would be the difference between our pipe surface temperature and our fluid mean temperature. So that large delta T means you're going to get the highest flux right at the entry of the pipe. But then as the fluid starts to heat up, your driving force, your delta T, gets smaller and smaller, which means you get less and less heat added each time. And that led us to an equation showing that our mean fluid temperature as a function of x will exponentially approach the pipe wall surface temperature. And we did all that with doing a differential energy balance. So we saw that if our fluid comes in at this mean temperature at the inlet, and it's traveling through a pipe that has this constant surface temperature, so if we were to plot the temperature as a function of x, our surface temperature is just constant in this particular situation. So we would see our fluid temperature, so we're going to have the biggest delta T here, which means our flux will be highest there. But as our fluid runs down the length of this pipe, that delta T gets smaller and smaller, so less heat is added to our fluid. So what this might mean from a practicality point of view is, let's say you want your fluid to be heated and you create this really, really long heated pipe and you maintain its surface temperature. There's going to be a point of diminishing returns where making that pipe longer and longer and longer isn't going to do very much for you, because the maximum temperature your fluid could reach would be the pipe surface temperature. Okay, I know that was sort of the last couple of lectures condensed down to just 5 minutes or so. So this is going to lead us to something that is really important, which is something called the log mean temperature difference. So I'm going to go through and carefully derive this. I wouldn't necessarily expect you to remember the derivation of it, but certainly the concept is going to be really critical as you analyze fluid flow through a pipe with constant surface temperature, or as you get into heat exchangers. This idea of a log mean temperature difference is really important. So if we looked at Newton's law of cooling, all right, easy question. What's the general form of Newton's law of cooling? Okay, H times A times delta T. That's Newton's law of cooling, okay? So what we're going to get to is when you have a fluid that changes in temperature over some spatial dimension in your system, we're actually going to use this different form of Newton's law of cooling, which is going to say that Q is equal to H times A times delta T with a subscript LM. So that LM means log mean. So it's still a delta T. Delta T is still going to be our driving force. However, because we don't have a constant delta T down the length of our system, we're going to need to use this special form of delta T. And you can see this by looking at this graph. As our fluid goes down, again, our delta T changes all along the way. So we have to look at what happens from the beginning of the pipe and do some sort of integration to the end of the pipe in order for us to really analyze how much heat is being added over the length of that pipe. So we're going to get into this derivation and help you understand what this log temperature difference actually means. So just oh shoot, and I didn't write those notes on an actual slide, so I can't go back to it now. So does anyone have a sense for how this derivation, how would we start doing this derivation? I want to make this point, so I'm going to draw this again really quick. If I I were really mean and had a homework question where I asked you to derive the log mean temperature difference, what would be your sense? How would you start? Okay, great. Yeah, thanks, Ivan. So Ivan thinks there's going to be some form of integration. So let's think about that. So if we were to take this long pipe, and again, this is just a graph of our temperatures. This is our mean fluid temperature as a function of x, and this is our surface temperature, which we're assuming constant. So integration is a great way of thinking about this. So if we wanted to look at just a small sliver of this pipe, we would look at this delta T. So in that small sliver of pipe, would it be a good approximation to assume that that we can just use a regular delta T there? Delta T is constant. It would. And if it wasn't a good approximation, you can just make that sliver even smaller. So just in that little tiny space, we could apply Newton's law of cooling locally. So we could use the flux form of it, for example, and just say the flux is equal to H times Ts minus Tm at that particular x. So we could certainly get the flux at a particular point, or maybe we could do some sort of finite difference approximation and assume that our mean fluid temperature is constant just in that one little section. So an integration would be something like doing this a bunch of different times, breaking up our pipe into a bunch of little sections, calculating the flux, or using like you could also use a differential form of this. So you could say the differential amount of heat you add in that little section is equal to H times the perimeter times Ts minus Tm times dx. So by doing these little small energy balances and figuring out what your differential amount of Q is, and you could then integrate all of the Q's to get your total amount of heat added from the beginning to the end. So that's really where this comes from. It comes from the fact that our delta T is changing down the whole length of the pipe, so we really can't just say, for the entire pipe at least, we can't say Q is equal to HA delta T, because our delta T from pipe surface temperature to the mean fluid temperature is different at every point along the pipe. So we've got to do some sort of integration. Yeah?
What's that P again?
P is the perimeter going around the pipe. So if it were a circular pipe, it would just be 2 pi times radius. So that if we took the perimeter around the pipe, so we took the perimeter around the pipe and multiplied that by dx, or the thickness of this differential element, that would give us a surface area over which heat transfer happens. And so that would be a more kind of closer to a standard form of Newton's law of cooling. Okay. So I'm just trying to get this concept sinking in. This is the reason we can't just apply Newton's law of cooling blindly. There's got to be some sort of integration that happens. So I'm actually going to, this is going to be somewhat repetitive to our energy balance when we solved for the temperature profile. If you remember from last time, we derived our mean temperature with respect to our surface temperature, and that gave us that exponential form. So now what we're going to derive is the total amount of heat that occurs, the total amount of heat that goes into our fluid over that same distance. So we're going to start similarly, but we're going to use a little trick here. Okay, so if we had this long pipe, so our first step would be to draw a control volume around a differential element, and this differential element would be delta x meters, or delta x units of distance thick. So we would apply an energy balance. So this is going to be, some of our assumptions are going to be this is at steady state, and also we're going to use a constant h, or we could use an average. So we're assuming that the flow would be fully developed, or that we're using an average of some sort, and that our heat transfer coefficient doesn't change as a function of x down the pipe. Okay, so to do this energy balance, we would have our accumulation would be 0. We're going to have an in term. So how is energy getting in to our little differential element? So we're going to have energy coming in from the previous node. So if there were another node here, we'd have fluid coming in from there. So that fluid is going to carry energy with it. So we would cover that in our energy balance. Okay, so how would we write an energy flow term if you have energy being transferred by fluid flow or advection? Okay, say that louder, Titus. Great. So we get m dot times Cp times our mean temperature evaluated at x. So there's also going to be an out term here, an advective out term here, which is going to be, again, m dot Cp. Now it's going to be that mean temperature evaluated at x plus delta x. Okay. So this tells us, this mCp delta T term tells us how is energy flowing as a function of just what's coming in with the fluid and leaving with the fluid. How else is energy getting into our system? Say that again? Okay, from the pipe wall. Great. So we have this pipe wall at Ts, and let's just say that it's a heated pipe. So how do we write that particular in term? So here, we're looking at just a differential element, so we can just apply Newton's law of cooling, because we're assuming that delta X is so small that there's not really going to be a substantial temperature change just over that delta X. And eventually, we'll shrink delta X down to 0, and this would be a perfect application of Newton's law of cooling. So here we would have H times the perimeter again, times delta X. And then we have our temperature difference here. So that's going to be our surface temperature from the pipe wall minus our mean temperature. Okay. So then we would divide by delta X. And we would take the limit as delta X goes to 0. And we're also going to define this delta T. This will make the differential math a little bit easier. Yeah, Ivan, do you have a question?
What's that Tm on the thing we just said? That Tm right there.
Here?
Is that the temperature of...
You're talking about this guy?
No, but actually in the convection.
Oh, here?
Down, yeah, like is that the temperature of the
fluid?
Yeah,
that would just be the temperature of the fluid inside of here.
Node, okay.
Yeah, so it would be the same as this temperature actually. We're just assuming that within that node, it's a constant uniform temperature.
Okay.
So that's just our fluid temperature at that, measured at that particular X. Okay, so we're going to define our delta T as Ts minus Tm. This will just make the math a little bit easier. So once we do these steps, I'm going to go, you guys can do this on your own and go through the individual steps. We end up with an equation that looks like this. D delta T divided by delta T is equal to minus H times our perimeter times dx divided by m dot Cp. Okay, so this is the same point we got to before when we were solving for the temperature profile. So we're going to apply a little trick here in a moment. But first, what's the basic form of the solution to this problem? What function are we going to see? We won't see exponential yet. When we do this integral, that's going to be natural log showing up. So in this particular case, we want to get the total amount of heat being added to our system from the beginning of the pipe to the end of the pipe. So we're going to do this integration from the beginning of the pipe to the end of the pipe. So I'm going to do a definite integral here and say, do this from delta T at the inlet to delta T at the outlet. where delta T at the inlet would be defined as our surface temperature minus our inlet temperature. And our delta T at the outlet would be defined as our surface temperature minus our outlet temperature. So here is where we would, at the end of this pipe, is where we would measure TMO. So how would we actually go about getting that outlet temperature? It's not 0. How do we know what temperature our fluid is going to come out of here? If it's a really, really long pipe, that'll eventually get close to the surface temperature. But we just, in the previous lecture, which I realized was like 10 days ago, we actually derived that. So we could use this equation and just plug in L for X, and that gives us our outlet temperature. So we can use this equation from a previous derivation to get our outlet temperature, and then we can go plug that in here to get the value of this integral. So we're getting there. Okay, so we've got this equation. This is going to be equal to, because we're integrating from our inlet delta T to our outlet delta T. On this side, we're going to integrate from 0 to L. So we end up with an equation that looks like this. So the natural log of our delta T at the outlet minus our delta T at the inlet is equal to minus HPL all divided by m dot times Cp. Okay, so we're going to leave this in this form for a minute. So there's another concept that we'll have to master. If we wanted to measure, let's say this is where it gets there's a couple of threads to follow here. If, let's say we knew our mass flow rate, we knew our heat capacity, we knew our inlet temperature, and we knew our outlet temperature, how would we go about calculating the total amount of heat that was added to our fluid? Okay, Q is equal to m dot Cp times our outlet temperature minus our inlet temperature. So this is another very simple, very important equation. Raise your hand if this form of this equation looks familiar to you. Okay, raise your hand if this is just totally coming out of left field and you've never seen anything like that before. Okay, so you guys know this. Enthalpy, so m dot Cp times our delta T would give us the total amount of heat added to our fluid. So now what we're going to do is we are going to make a substitution. So you can figure this out on your own, but this, if we wanted to put these two temperatures in terms of the delta T's, because our delta T is surface temperature minus fluid temperature, those get flipped, but we would see that this would be the same as m dot Cp times delta T out minus delta T in. So we picked up a negative sign, and that comes from the way our delta T's are defined, where it's surface temperature minus the actual fluid temperature. Okay, so now what we're going to do is we are going to, we see that, so we have this equation that is coming from the differential energy balance on our system, where we're trying to integrate what's happening from the beginning of the pipe to the end of the pipe. Then we have this second equation, where if we can measure our mass flow rate and our delta T's, then we know how much heat is being added. So the common variable here that we're going to take advantage of is the combination of m dot times Cp. So we would actually solve for m dot Cp is equal to Q over negative delta T0 minus delta Ti. So I'm just solving this second equation for m dot Cp. Then I'm going to take this guy and plug it into here. So we end up with this equation, our natural log of delta T at the outlet divided by delta T at the inlet. Our negatives, so there's a negative in this equation, there's a negative in this equation, those will cancel each other out. So this is H times P L divided by, multiplied by this special temperature difference. Okay, then we just solve this for Q. So if you've gotten lost along the way, we'll go back and put some meaning to this. So Q, so before I proceed, if we did the perimeter multiplied by the length for the entire pipe, what's the meaning of that? That's the total surface area of the pipe. So let's just plug in pipe surface area there. So where this pipe surface area is just P times L. Okay, then we have delta T at the outlet minus delta T at the inlet, all divided by the natural log of delta T at the outlet times delta T at the inlet. Okay, so that's pretty much that. If we knew the heat transfer things and we knew our outlet temperature, this would be one way to go about solving for Q. And it turns out that the combination of knowing these two different things can be really helpful to us. We might end up in situations where we have two different ways of calculating Q, and so we'll have two equations, we might have two unknowns that we'll need to go and solve for. Okay, so examining this equation more carefully, so Q is equal to H times A, and then we have all these kind of strange manipulations of temperature. What does that equation look like, though? HA delta T. Okay, so it kind of looks like Newton's law of cooling, and in fact, this is just a modification of Newton's law of cooling for when you have your fluid changing in temperature as it goes down the length of your system. So we're going to take this part and define that as the log mean temperature difference. So our delta T log mean is defined as delta T at the outlet minus delta T at the inlet, all divided by the natural log of delta T at the outlet over delta T at the inlet. Okay, so now Newton's law of cooling can just be expressed as Q is equal to HA times delta T log mean. And you'll also see this, notice, you'll see people call this the LMTD, the log mean temperature difference. Okay, so I don't necessarily expect you to remember all the nitty-gritty details of that derivation, but the concept is extremely important, where when you have fluid flowing through a system and that fluid itself is changing in temperature, you can't just blindly apply Newton's law of cooling. Now you have to do this integrated form of Newton's law of cooling, which is going to account for each of the individual Q's, if we were to break up our pipe into small sections, and basically does the integration. So through doing a differential energy balance and using this other change in enthalpy is equal to our Q, we're able to arrive at this equation.
What were the assumptions we used again to derive that? Like, we had certain.
So we assumed steady state. We assumed that you basically have to assume either an average heat transfer coefficient or a constant heat transfer coefficient through the pipe. If you get a heat transfer coefficient that varies in a weird way, this won't quite work, because weird things will be happening as you go down the length of the pipe. So a steady state, constant or averaged heat transfer coefficient, and then constant pipe surface temperature. Although this is also going to apply when we talk about heat exchangers, and when we have two different fluids flowing, this will still apply. Okay, any questions there?
So that's the term for Q for those specific assumptions made for this specific example. It's not like
Yeah, it's fairly broadly applicable.
it is,
Yeah, and we'll actually do this when we talk about heat exchangers. Actually, when Dr. Pershing talks about heat exchangers, you'll hear him mention the log mean temperature difference quite frequently, I think. Okay, any questions? So it's important to know, so when you have a fluid that's changing in temperature down the length of your system, you can't just use a simple delta T. You have to use this log mean temperature difference. And that's because your driving force, i.e. your delta T, is changing as a function of distance down the length of your system. And we'll see this in a different form again when we talk about heat exchangers. This would actually apply to when we had external flow. When you have flow through like banks of tubes, that would apply, or flow through a packed bed. It's just that your surface area will be different. It won't just be the inside diameter times length of a pipe. It would be the outside diameter times the number of pipes you have if it's flow through a bank of tubes, for example. But this equation is quite important. Any questions? Okay, so this is sort of just a review of what we just covered. So our temperature profile is going to look something like this, and then the total amount of heat delivered to our fluid is going to look like that. So our temperature, our mean fluid temperature, is going to exponentially increase it's going to exponentially approach our surface temperature, and then to get the total amount of heat added to our fluid, it would be H times the total surface area times the log mean temperature difference. And you can see the log mean temperature difference. This is one, don't necessarily need to commit this to memory, but you'll definitely want to get a lot of practice using this and knowing how to apply the different delta T's. So this diagram kind of makes it easy. Delta T at the inlet is defined here. Delta T at the outlet is defined here. Okay, any questions there? So, let's see. Okay, there's a special case. So let's say that our pipe temperature isn't necessarily uniform. Let's instead assume that we have flow going down the inside of a pipe, and then on the outside of the pipe, we have another fluid flowing in cross flow against it. So how would we handle that type of a situation? Average temperature, okay. Not quite. I'll give you a hint. It has to do with thermal resistances. So this is where the thermal resistance method sort of converges with this stuff we're talking about in convection. And this is really important stuff for analyzing heat exchangers. So if we had this uniform external fluid temperature, we've got a pipe, and we have fluid flowing through that pipe here. Then we've got a different fluid flowing against that pipe. And let's assume that that outer fluid has a constant temperature. The analysis is basically the same. And you can see this temperature profile looks very similar functionally, except in place of H, we're using U. Who remembers what U is? Yeah, James? Overall heat transfer coefficient. So that's just basically what's happening in this situation. There's convection happening on the outside wall, there's convection happening on the inside wall, and then there's also conduction happening through that wall. So we have to factor in those other thermal resistances. So we have to get from our T infinity, so notice we're no longer using surface temperature in this equation, we're using this outside fluid ambient temperature. So we'd have to solve for our U that gives us, our U that factors in the two convective thermal resistances and the conductive thermal resistance. But then the equation would basically become the same. We're just factoring in these other thermal resistances. So when you're talking about heat exchangers, you'll typically deal in terms of U, the overall heat transfer coefficient. You'll have two fluids. So one is going through a pipe, the other one is on the outside of that pipe. So there's convective thermal resistances for each of them, and there's a conductive thermal resistance through the pipe wall. So you're going to have to back solve to get U instead of dealing with the H's. Questions there? So do you remember? So let's go through this again. I'll try and do this from memory if I can. So let's say we have this situation happening. We got a pipe here, and so we've got an H in and an H out. Let's for now, let's assume we have a thin-walled pipe. So we're basically going to neglect the conductive thermal resistance. So if we wanted to get heat from inside to outside or vice versa, how would we go about doing that? So we'd get our total thermal resistance. These are going to be two resistances happening in series. So that's going to be this convective thermal resistance on the outside plus the convective thermal resistance on the inside. So we would get our R total, and then Q would be, actually, so this is going to be 1 over H out times A plus 1 over H in times A. So you might want to go back and review thermal resistances because these are going to be really important. Okay, then we get our Q is equal to our, let's assume it's a heated pipe, so our T out minus our T in divided by the total thermal resistance. We could also express that as UA times our temperature out minus our temperature in. So here this U would be our overall heat transfer coefficient. So this combination UA is going to be equal to 1 over the total thermal resistance. So to calculate our UA, so UA would be 1 over H out times A plus 1 over H in times A, and take the inverse of those. So this is where thermal resistance method converges with our analysis into convection. So instead of just assuming that we have a pipe temperature that's constant, we can actually look at the interactions of the internal fluid with the external fluid, but end up with equations that are quite similar. And you can notice even the different functional forms of these equations. Here we've got our UA, which is equivalent to 1 over the total thermal resistance. Questions there? Raise your hand if you're lost here and have no idea what's going on. Okay.
I have a question.
Yeah, please.
So, to find the H to solve for our Q total, right? So we had to find like our Q total when we were given everything else except our H values, right?
Yeah.
We had to find the mean log. What is the mean difference? Mean log that we just went over, right? Is that the H we have to?
So to find the H's, you would use convection correlation. So those would be a function of Reynolds number and Prandtl number. And then you could, so the H's themselves should be, you wouldn't need to solve for the outlet temperature first. You could just calculate the H's. You might have to take a guess value at temperatures to evaluate thermal properties. Let's just back up for a second. To find those individual H's, so this H, so this is going to be from a correlation. This is cross flow across a cylinder. So from chapter 7, you should be able to find the appropriate correlation to give you H. Then this is flow through a circular pipe. So from chapter 8, you can find the appropriate correlation to give you fluid flow through a pipe. And then you would do that rule to find your UA term. We can chat afterward if you still have questions. Okay, so if you have a fluid, so I kind of jumped to this part when we were deriving the LMTD, but we've basically come up with this equation. So if we've got a fluid coming in here at our mean temperature at the inlet and leaving at our mean temperature at the outlet, we can express Q as Q is equal to m dot Cp times TMO minus TMI. We can also express Q as HA times delta T log mean. So in some cases, we may have our outlet temperature is unknown, and we may use these two equations to go simultaneously to go and solve for our outlet temperature. So frequently, being able to do balance energy like this can be a really handy tool. So basically what we're saying is all of the energy added to our fluid is equal to whatever comes in by convection down the whole length of the fluid. So this, being able to equate these different things can come in really handy. And in the future, when we talk about heat exchangers, there will be a third equation added to the mix. So let's say this were just a simple two-plate heat exchanger, and we had a hot fluid here exchanging heat with a cold fluid. Then we could, the energy exchange between them would be HA times delta T LM, which would be equal to m dot Cp times T outlet minus T inlet of the cold fluid, which would also be equal to m dot Cp times T inlet minus T outlet of the hot fluid. So these are just some very simple energy balances that you can do so that you can get equations. You can use these equations to solve for unknowns. So if there are certain pieces of information that aren't given to you, you can apply energy balances like this. So this is basically two equations. So you get, well, two independent equations. You get HA delta T log mean is equal to the enthalpy change of our cold fluid, and that's also equal to the enthalpy change of our hot fluid. And you do have to specify the mass flow rate and Cp would be specific to the cold fluid and the hot fluid. Okay, any questions there? So we got 5 minutes left. I really want to finish this chapter today. So we're going to go back to this process if we want to find our H now. So we have to go back to these correlations. We have to look at our geometry of our system. Is it a pipe? Is it an annulus? Is it a square channel? We calculate Reynolds number. We determine if our flow is laminar or turbulent. We evaluate our Prandtl number. And then we plug these into the appropriate heat transfer correlations again to find the Nusselt number. So the Nusselt number could be local or average. Typically, we'll make the assumption that our flow becomes fully developed, and we'll just use a constant. So that could represent an average, and we'll sort of ignore the entry length. So once we have our Nusselt number, we'll back solve to find H. And then once we have H, you can plug it in to find things like outlet temperature or total heat added to the fluid from the equations. So for the rest of this chapter, we're basically just getting into different correlations. So I'd encourage you to go back and review these slides, because we've sort of covered the important conceptual things. So when you have laminar flow in a circular tube, a really interesting thing happens is that our Nusselt number becomes just a constant. So when we have uniform surface heat flux, that constant is 4.36. So we take that 4.36 and back solve to find our H. When we have laminar flow with a uniform surface temperature, that Nusselt number is 3.66. When we have turbulent flow, we would use an equation that looks like this, where Nusselt number becomes a function of the Reynolds number. So this is the Dittus-Boelter equation. I'm asking you to use this particular form of the equation in your homework for this problem 6 that we'll be doing on Wednesday. If you want to get a little bit more rigorous, you can factor in the wall roughness and the friction coefficient and use this other Nielinski correlation. So when you are dealing with entry regions and you want to calculate your heat transfer coefficients in that entry region, you would use something called the Gratz number. I typically won't worry too much about that, but you can see that your heat transfer coefficient in that entry region might be changing, but eventually it'll level off. So if you have a really, really long pipe, you can just sort of neglect what's happening at the beginning and just focus on what's happening at the end of the pipe. So yeah, we're going to skip through some of this stuff. I'd encourage you to go review this stuff. some important things are often there may be some iteration that happens where a lot of your thermal properties, like the Prandtl number and the thermal conductivity, might be a function of temperature. Well, if your temperature is changing down the length of the pipe, at what temperature do you use to evaluate those properties? So the rule of thumb would just be to take the average temperature between the inlet and outlet. Well, that's where iteration might come into play, because you need those properties to evaluate your equation so you know the outlet temperature. So you may have to take a guess on the outlet temperature, use that mean temperature to calculate your fluid properties, and then iterate, take a second guess, and do this iteratively. I promise I won't give you one of those on an exam, though. Okay, there are different correlations if you have non-circular tubes. You can look these up in a table. Okay, so just real quick, where would you see a tube or a channel that is square or rectangular? Say that again? Air ductwork. Yeah, air ductwork. Yeah, so you'd see that all over the place. This is really important, like for HVAC applications. So you've noticed there's a triangular one. Where might you see a tube or channel that has a triangular cross section? I really don't know why you would do one like that. Okay, so this one is actually a little bit more important. This is called an annulus. So this is the space that, if you had two concentric tubes, this would represent the space between the outer tube and the inner tube. So where might you see something like that? Yeah, James? A shell and tube heat exchanger? Close. This is actually called a double pipe heat exchanger. Yeah, shell and tube actually gets quite a bit more complicated geometrically, but great. In a heat exchanger, so James nailed it. So you might have one fluid that's hot and another fluid that's cold. So the hot fluid might be flowing in the annulus, and the cold fluid might be flowing just through the inner tube, and those two would exchange heat. So this is actually kind of a more important geometry. And there are different correlations for that. But that takes us to the end of Chapter 8. So thank you very much. Remember to come prepared on Wednesday to do this flipped classroom, and we'll see you then.